Jackie, who will tell us about, I don't know what you're
gauging spacetime.
Gauging spacetime inversions.
Okay, so this is work with Akiro, Newton's Hollow. And of course, thank you for the invitation. It's nice to be back. I was thinking it's been at least 6 years since I was here, so it's nice to see everybody again. Although I guess a lot of the people have turned over in 6 years, but some people are. I'll give for this talk I'll give a disclaimer, which is that not only am I going to violate causality, I will also modify quantum mechanics. So if at any moment you feel the desire to sort of stand up loudly and shuffle out of the room and protest, you're welcome to do so. I have 10 years. Okay, so this talk is going to begin with the tension. So before I tell you the tension, I just want to establish some notation. So when I write CRT, okay, that's rotation by pi in Euclidean signature. Okay, so people often combine this with a spatial rotation and call it CPT, but that only works in even dimensions. Anyways, that just obfuscates the issue. So the thing that's a symmetry is a rotation by pi, and in Euclidean signature, that's the proof of the CRT theorem. So I'll say CRT in this talk from now on. So now let's say the tension. It's not really a tension, but it's maybe at first seems tension between two things. So one is that CRT is always a symmetry. And two is there are no global symmetries. So let me just comment briefly on both of these things. So of course in quantum field theory this is just true, it's a theorem, it's the CRT theorem, proven in ancient times. It's less clear that in quantum gravity this should always be true, because we don't have a theory of quantum gravity in general. In ADS-CFT it's certainly true because the boundary theory is a quantum field theory, so that obeys the CRT theorem. In string perturbation theory it's also true because you can do a rotation by pi in the target space. Okay, and that's a symmetry to all orders of the genus expansion. So for this talk I'll just assume that this is true in general as a statement about quantum gravity. Never heard a good argument to the contrary. The second thing I've given many talks. Yeah, go ahead.
Are we supposed to think of a particular setting here, like a flat, or are we talking about quantum gravity generally?
Completely generally, yeah. So it's a little bit delicate to say exactly what I mean. And I'll say a little more about in a situation where there's no boundary what exactly it means to say that CRT is a symmetry.
Yeah, I was wondering if you could comment on what this rotation exactly looks like.
Well, yeah, one way to say it is if you think about kind of what manifolds you're allowed to sum over in the path interval, the manifolds are covered in patches, and there are Gaussian functions for the patches, and those should be allowed to include rotations. In Euclidean signature rotations by pi.
So you're rotating between different format patches?
Yeah.
Between
Yeah, I think that will be more clear as we go on. So for now, let's just leave it a little bit fluffy what we mean when I say it's a symmetry. For one thing, I have to at least say the next line before we're going to be able to define it precisely, right? Oh yeah, go ahead.
I also have a conceptual question. So you're currently focusing only strictly on relativistic field theories?
Yes, that's correct.
Even in the case where, for example, you can have a bulk holography with a boundary theory, which is an relativistic CFT or non-relativistic field theory, therefore doesn't have to be CRT variant.
Yeah, so you can turn on boundary conditions that break Lorentz symmetry.
Or you can start with boundary with a theory which did not have Lorentz invariance in the first place.
Yeah, so my philosophy would be that in the bulk, the Lagrangian will look Lorentz invariant and may be broken by the boundary conditions. But yes, if you want to...
So that's our restriction.
Yeah, let's just say relativistic theories of quantum gravity. Yeah. So, so yeah, that's assumption number one. Assumption number two, I'm not going to try to justify this. I've given enough talks about this. I'm sure you've heard about this before, this idea that in quantum gravity there are global symmetries. There are lots of arguments for that. If you want to hear one of them, ask me after the talk. So, of course, in order for these two statements to be compatible with each other, we see that CRT has to be a gauge symmetry. That's how it's the only way that we can avoid the tension. And so the goal of this talk is to explain in more detail what this sentence means, tell you some of its more potentially surprising consequences. One thing I'll say, just to kind of give you a hint that this might not be such a obvious thing that, a thing that obviously makes sense. So we can also say, so for example, so CRT is always a symmetry, but just to simplify the discussion for a sec, let's imagine that time reversal is also a symmetry. So that may or may not be true, but let's just assume it is for a sec. Right? So then if you say that time reversal is the gauge symmetry, it means that there are valid configurations of the universe where you go on a little journey around a spatial circle, and when you come back to where you started, the direction of time was flipped. Okay, so a geometry of that type is the Lorentzian Mobius strip in 1+1 dimension. So that's a perfectly fine Lorentzian manifold, but it's not time orientable, and so you could view this as a non-trivial background field for time reversal symmetry. Oh!
You need to stop the jokes that are apparently happening.
Yeah, is your car working now?
Yeah, I only come. It's working.
That's good. It can be a bother. So, if you look at something like this, it's not maybe so clear that physics should make sense in a geometry like this, right? And so, if we're going to accept this logical implication, then we're going to have to learn how to live with geometries like this. And so most of this talk is going to be sort of learning to live and love geometries like this. In literature, in fact, there are claims that geometries like this don't make sense. For example, that you can't define quantum field theory in geometries like that. That's a claim in the literature of algebraic field theory. Okay, and so I'm rejecting such claims to this talk.
Sorry, is that claim for all theories or just fermionic theory?
Even bosonic theories. Just to give you a hint of the complaint, like a complaint you could make is that in order for the quantum theory to make sense, you have to define canonical commutation relations, right? But when you say phi dot, is it this way or that way? And if you go around the circle, it seems like there's you meet some discontinuity in this commutator. So that's an example of a criticism that has been given against doing quantum field theory on this geometry. So what I'm going to do is argue that in fact this does make sense. I'm going to give an example, an AES CFT, where you have to include something like this to match a boundary calculation. And then I'll give some discussion about what this means in the context of quantum cosmology where there's no asymptotic boundary. Okay, so that's kind of it for the introduction.
Sorry, I have a
Yeah.
conceptual question. So when you say CRT is a gauge symmetry, does it mean some observable on this background is the same as an observable on a usual background?
Let me go on, I'll define what it means. Yeah. Yeah, somehow part of the goal is to understand what this means. Okay, so let's first do a warm-up. So let's start with gauging discrete internal symmetries. So that's something which, in principle everyone should know, but my experience is not everyone knows. So if you don't, sorry, I'll be bored for 5 minutes while I'll explain how this works. So I'll first say the math definition and then try to unpack why it's the right definition. Okay, so if you have a quantum field theory with a discrete global symmetry group G, so let's start with a global discrete symmetry group G and then turn on a background gauge field for for it, right? And then to gauge the symmetry, we should sum over the background gauge fields. But let's first think about how to turn on a fixed background for a discrete global symmetry. Okay. So the definition of a background gauge field on a manifold. So here we're on a space-time manifold M with a global symmetry group G, which we'll think of as discrete. So the definition of a background gauge field is that you have a homomorphism, W, from the fundamental group of M. And if you really want to be fussy, I should pick a base point, although of course it doesn't matter which point I pick, as long as M is connected, to G. And then actually that's not quite right. I'm supposed to quotient by conjugating the image of the homomorphism by an element of the group. Okay. So that's the math definition. Let me now try to say why that's the right definition. So what this W does is for each circle in M, it tells you the holonomy if you move a charged particle around the circle. Right? So elements of pi 1, right, the fundamental group, are loops that start at x naught and end at x naught in M. Okay, so here's M, here's x naught, and we can have some loop that starts and ends at x naught. And then what this W tells you is it tells you if I take a charged particle, or a field that's charged in some representation of G, and I move it around the loop, then this tells me which element of G it gets multiplied by after I go around, right? So this is usually called holonomy in gauge theory. And then the reason you have to quotient by conjugation is because I could do a gauge transformation here. And then that would just conjugate, like, so if you think of a Wilson line, right, it gets conjugated, or a Wilson loop that's not traced over, it gets conjugated by the group elements at the endpoints. And then it has to be a homomorphism because if there are two cycles and I go around this way and then I go around that way, then you should just multiply the holonomies. Okay, so that's why it's a homomorphism. All right, any questions, comments, concerns?
Yeah, I want to complain. So you're thinking of this as a map from the holonomy to the group, like the image of the holonomy you're quotienting by the actual conjugation, right?
Yeah, at x naught. Yeah, so this quotient is the gauge transformation at x naught.
Yeah, I think that's not for a general group. That's not that's not a complete description. So
I think it's a theorem. Yeah, there's some theorem about covering spaces, right? So yeah, I mean, the real definition is that it's a principal G bundle over M.
Yeah.
Okay, that's the real definition. But then for a discrete group, that's always a covering space of M, where there's.
So the objection I'm making to is the idea that it's completely classified by Wilson.
But
So
I think there's a theorem about that.
Well, I think I'll give you a counterexample. I think I wrote a counterexample in a paper once. We can discuss this.
Let's talk about it later. Yeah. I mean, I didn't make this up, right? Like it says this in the paper of like Witten from 1988, right? So I didn't just make it up. Yeah. But I'm happy to be convinced that this thing that everyone says is wrong. I sort of sketched a proof of it myself, but I can't say I was like super careful. Okay, but I think, yeah, it's kind of natural to say that you have a holonomy around each cycle, and then that's kind of what it means to have a background gauge field for a discrete symmetry. And you can think about, okay, so that's kind of maybe too mathy for some of you, so let's try to make it more concrete. So when you have a global symmetry, what do you really have? You have a codimension 1 surface operator, U of G, associated to each element of the group. And for an internal symmetry, U is unitary. Okay, so for each sort of d-1 dimensional surface in the space, you can put a U of G on it. And that's some operator, and if you conjugate operators by that U, that's how it defines the symmetry transformation. And so the way you turn on a background gauge field is you have some space that has some pi 1, so it has some loop. And then you sit this U of G on the sort of Poincare dual cycle to the loop, so that here the holonomy is going to be this way. And then if you take an operator here and you kind of drag it around the circle, then you see it gets kind of stuck on the operator here. So there's some process where you kind of have to do this, right? And then you kind of keep going. And at some point you can put this back here, but now this has a little dash around it. Okay, and then you can move this thing around. Okay, and so now here I started with O times U of G, and when I finished it around, I ended up with some D of G times O times U of G, where this D is some representation into O transforms. So the way you turn on a background gauge field is you kind of sit these symmetry operators on the various dual cycles to the loops, and that tells you what the Hall limits are. So sorry, that's a little bit formal, but you see we're going to use it in a minute. Now, to gauge the symmetry, then we're supposed to sum over the Hall limits. So to make this a little more concrete, let's take M to be a torus, two-dimensional, and let's take G to be some Z2 symmetry. Then if we gauge the symmetry, then what we're supposed to do is divide by the volume of the gauge group, and then we have a sum over kind of four different background gauge fields. So we could put the symmetry operator that way. We could put it this way, or we could put it both ways. And so if you like, in this background, the holonomial is trivial in both directions. For this background, the holonomial is trivial going this way, or sorry, not trivial going this way, but trivial going that way. For this one, it's trivial going that way, and for here, it's, sorry, non-trivial going that way, and for here, it's non-trivial in both. And if you care about these kind of things, when you say that it's not anomalous, you mean at the crossing here, nothing funny happens. Okay, that the crossing is unambiguous. If something happens at the crossing, then we say there's an anomaly, and you're not allowed to do the sum. So we can interpret these in the following way. So the sum of these two, we say, is a projection onto singlets in the original Hilbert space of the theory with where it was global symmetry. And then if you look here, so here I'm thinking of time going up, right? So then here, because this operator is here, you've changed the Hilbert space of the theory. So if I cut it here, I have to cut through that operator that wasn't there in the original Hilbert space. And so this is called the twisted sector. And so then this is, again, a projection onto singlets, but now in the twisted sector. Okay, so that's the kind of Hilbert space interpretation of the gauging. So you have to restrict to singlets, but then you also have to include the twisted sector, and in the twisted sector also restrict to singlets. So for people who are familiar with the string world sheet, this is usually called orbifold or something, right? This is something that we do all the time. So an example of this would be a Z2 orbifold on the world sheet. Another example of this, which is kind of fun, is the Ising model. So people often say that the Ising model is a Friedmeier on a fermion, but that's actually not quite true. It's a Friedmeier on a fermion with fermion parity gauged. And so these sum over four sectors are the four terms that you sum over in the Ising model with the periodic and anti-periodic boundary conditions and so on. So in the Ising model, fermion parity is gauged, so it's not actually a fermionic theory, it's a bosonic theory. All the states have zero fermion number. Okay, any questions about this? That's the end of the review. Sorry, a bit dry, but we have to go through this because we use this language. Last time I gave this talk, somebody wanted to fight with me about the Ising model for like 5 minutes. Okay, so that's for the internal symmetry. Now let's think about backgrounds for space-time symmetries. Okay. So in the paper we do continuous things, backgrounds for translations, rotations, etc. Of course that is turning on the background metric is how we usually think about that, and that's correct. But you can also think about it in this language if you want to. I will go straight to space-time inversions though. So as a first example, this one I'll mention quickly, but I'll just mention it because there's a kind of fun conclusion. So let's first talk about backgrounds for R. So R is for spatial reflection in one direction. And so here, for simplicity, I'll just do a free scalar of 1 + 1 dimensions. So the R symmetry acts on phi of t and x as phi of t and L minus x, where here I'm thinking of myself as being on a spatial circle of circumference L. Okay, so that's the L here. So that's the symmetry. Now let's turn on a background gauge field for it. So this is kind of fun. So, well, you can certainly, so the first two things just project onto states that are invariant under the reflection, so that's not too exciting. It's more fun to think about the third thing there. So that's something where if you go around from 0 to L, if you want to say that you put the symmetry brane here, so you get a holonomy for spatial reflection as you go around, then that's saying that if I go around the circle once, then instead of just coming back to myself, I come back to myself up to this spatial reflection, which I can rewrite as phi of t and x is equal to phi of t and L minus x. So if you think about what that does to this picture, it just removes half of it. Okay, because it's kind of saying that whatever is here is the same as something over there, so it gets rid of half of the degrees of freedom. And moreover, if you stare at this equation for a little bit, you see it actually creates boundaries here. So this creates a situation where I have actually Neumann boundary conditions at both ends. Okay, so this is an open string, if you're thinking in string theory. Okay, so what this says is that if you try to gauge world sheet parity, then there are twisted states which are open strings. So that's a statement that actually has been discussed in the literature and string theory in the past in the 80s. There are various fights about it on both sides. Yeah.
I'm just claiming the authorship of that in the 80s.
Oh, you want to say that? Okay, yeah, I found a paper by Sanyavi who said this. Is there also one by you?
Yes.
Okay, great. Yeah, I would love to find that, yeah.
Yeah, that's where oriented faults come from. Oriented faults and the brain says twisted states of oriented faults.
Yeah.
That's exactly the origin.
Yeah, so I found, like, for example, in Polchinski's book, he says, he has this sentence where he's like, some have said that open strings are twisted states of gauging world sheet parity, but I don't think it's true. And so I was kind of, I couldn't, he didn't say who the some are, but then I found some papers about it, but I'll try to find yours also. Yeah, so I thought that was kind of amusing because, for example, if you just look at the string scattering, right, it seems like a closed unoriented string theory is fine by itself, just in perturbation theory. It doesn't seem to need open strings, but this would be saying that it needs them. Which I think is not, I mean, that's true, for example, you to go from type 2b to type 1, right, you get open strings, and I would think of it as an illustration of this. But yeah, at least some people have resisted that. Kumran was fighting with me about it. Emil also told me, Martinek also told me he thinks it's true, so I don't know, I've got it in a range of opinions. Okay, so anyway, that was still somewhat conventional. Now let's do something more scandalous, so let's do the background for T. So again, it's something like this, right? So the first two things are just going to project onto T invariant states. That's not too surprising. The more funny things are these twisted sector states. And indeed, one of them is this thing that I already wrote, the Lorentzian-Mobius strip. So let's talk about that. Okay, so this I would say is an example of a twisted background for time reversal. And so if we're going to gauge time reversal, we're going to have to sum over things like this. In particular, we're going to have to try to make sense of quantum field theory in states like this. So let's just write out the boundary conditions again now, right? So this says that phi of t and x is equal to phi of t and x plus L is equal to phi of minus t and x. Right? That's what this identification says. So first, let's now address the complaint about the commutator phi and phi dot from the axiomatic field theory literature. Okay. The complaint is that in order to impose the canonical commutation relations, I have to pick some surface here and say that surface is the surface where the commutator jumps discontinuously, and that breaks the translation symmetry of all the geometry. Okay. And so that's what people complain about. On the other hand, the same was true here, actually. So before I gauged the symmetry, when I just turned on the background gauge field, there was the symmetry operator sitting here, and it wasn't sitting there. And so when I move the operator across it that's charged, it can detect the location of that. It knows that it's here and not there. Once you gauge the symmetry, the ability to detect the location goes away. Because when you restrict to singlets, right, so of course singlet operators can't tell where the brain is. But when it's a background field, as it is here, then it's okay for charged operators to be able to tell where the brain is. And for time reversal, that's illustrated by the fact that the canonical commutation relation will jump as I go from here to here. So I think it's fine. Now, you could say, well, okay, come on, Daniel, let's just look at this. Like, how can this possibly make sense, you know, as any sort of causal or initial value kind of thing? You know, how could you imagine a Hilbert space on a slice of this crazy-looking geometry? Okay. Well, it's actually not so bad. So let's take the t=0 slice to start with, okay? And think about what's the set of initial data that's consistent with these boundary conditions. Well, it's really not too bad. So the initial data is that phi is periodic. Right? So if we said t=0, this just says phi is periodic with t=0. And phi dot is anti-periodic. So that's a reasonable set of initial data, right? I mean, that's not less initial data than you would have if you had just been on the ordinary cylinder. It's just that I made this one anti-periodic instead of periodic. And in fact, you can write down a complete set of solutions of the wave equation on this geometry so that you can have a solution for any initial data in this set. So classically, this theory is fine. It has a perfectly good initial value problem starting from the t=0 slice. You just have to be a little bit careful because to evolve to another slice, you have to make sure it's a good slice. So you have an evolution that takes you from that white slice to that yellow slice because you want to make sure that the slice is good going around. And so there are points that are not on any space-like slice. Like this point down here is not on any space-like slice because whatever you do here, the slice has to end up there. Okay, so it's not going to be space-like. So that's kind of a weird thing you live with, but nonetheless, there's a fine Hilbert space you can construct here, a representation of the canonical commutators and so on. There is, however, a subtlety. Sorry, let me pause and ask questions. So I promise there will be some surprising things coming soon, but I have to get through this background first. Already at this point, my experience is that relativists get very angry at me. Like Gary Horowitz came up to me and he said, "No, Daniel, come on. In any textbook in relativity, on the first page of the chapter about causal structure, it says that it has to be time orientable." So, you know, okay. Sorry. Sorry. There's an argument here that doesn't. So deal with it. There is, however, a subtlety, though. And this subtlety is the second part of why there was a lot of complaining about this kind of thing in the literature. Okay. And the subtlety is that there's no natural state. So let's try to think about why. So the most natural state that we would usually talk about in any quantum system is the ground state of the Hamiltonian. But here there's no time translation symmetry, right? Like there's certainly not a symmetry that takes this slice into that slice or into any other allowed slice. So there's not going to be a natural round state or eigenstates of the Hamiltonian. There's certainly a Hilbert space, right? It's just, you know, spanned by functions of phi as usual, right? And the discanonical commutation relations act on it. And so it's a normal Hilbert space, positive norm, etc. But there's no natural state you can write down. Now, at least what I just said maybe convinces you there's no natural pure state. What we usually do in that situation is we instead try to construct states using the Euclidean path integral. Right? So like, for example, for the Harlow-Hawking state or something, right? So also in cosmology, there's no natural notion of ground state, but you can say, well, I just do the no boundary path integral and construct a state that way. So let's try to do that here and see what happens. So what would be a good Euclidean state to write down? So let's take, now so this is Lorentzian, now this picture here will be Euclidean. Let's just construct some state where I put a kind of a phi initial here, and I put a phi final here. So I do a path integral like this, but then in order to make sure I prepare something that lives in this Hilbert space with these boundary conditions, I had better identify it like this. No, sorry, that's wrong. It should be this and then this. So this is certainly a path integral I can compute, right? It's a function of phi I and phi f, and it would certainly be natural to define this as phi f times some state, which I'll call rho tilde, times phi I, right? But of course it wouldn't be a pure state because these gluings mix the bra in the ket, right? And I have to sum over the fields of the gluings, right? So it'll be some sum of outer products of pure states. Now you might say a mixed state, that's fine, I don't really care, but in fact it's even worse. So it's not a state at all because it's not positive. Okay. So when I say that there's no natural state, of course the state, it's okay if it's mixed, but this should be a positive operator. And if we try to use the Euclidean path integral, we'll get something that's not positive. Now I want to stress that it's not because the Hilbert space is sick. This is the confusion in the literature of the algebraic field theory people. Okay? So just because you can't write down a natural Euclidean path integral that defines a positive operator doesn't mean that the Hilbert space doesn't have a positive norm. Right? The Hilbert space is fine. It's spanned by states like this, it has a positive norm. We just have to accept that there's no natural state and learn how to live like that. So the approach I will adopt for the rest of this talk is to just embrace things that aren't positive. Again, that's not because I'm modifying quantum mechanics. I said I was going to modify quantum mechanics, but it's not happening here. Okay? It's just that I want to have some reasonable set of computables that I can use to probe the theory, without having to make just some totally arbitrary choice of a state in the Hilbert space. And so what I'll do instead is I'll compute, expectation values, which are a trace of rho tilde times O, where O can be various things. But we just remember that these aren't really observables. I mean, the O's can be observables, but the rho tilde is not a state. But nonetheless, for example, I can compute correlators, I can put phi of x times phi of y here, I can study the algebra of the operators inside of things like that. Okay, it doesn't matter that the rho tilde isn't really a good state. So I'll call it a pseudo-state. That's actually, Justin Norrie suggested that term. I like it. I was calling it something stupid. He said call it a pseudo-state. So that's well. Yeah.
Is the reason why the state is not positive that the path integral is not reflection symmetric, or is that?
Yeah, it's related to that. So I'm going to give you a formula for this rho tilde and any 2D CFT in a minute, and then you'll see more explicitly that it's not positive. Okay. In fact, let me do that now. That was the next thing I was going to do. So in fact, let's work out the formula for this. So I can take this picture, right? And I can just redraw it in a different way. So I can take phi f here, and up and then down, down. But then I'll take the top half and just kind of flip it down like that, using the time reversal symmetry which we have. Okay. By assumption, right? This is background symmetry for T, so we have T symmetry. Okay, so then this top thing gets replaced by this, where now it's the time reverse, the phi initial here, with an up. And so if you look at this now, this is just the ground state on the cylinder, right? Let me put the phi I up here. Because now if you look at the gluings, right, these are glued the same direction, and these are glued the same direction. So this is the ground state of the theory on a circle that's twice as big. except I'm computing the wave function with t phi I here instead of phi I. And this is phi actually, sorry. So you can, at least in a CFT, right, then you can relate this to the Rindler decomposition. So in general quantum field theory, this is kind of as far as you get here. You just say, it's the ground state on a circle, okay. But if you're in a CFT, then the ground state on the circle is conformally equivalent to the ground state on the line. And the ground state on the line we understand using the Rindler decomposition, okay. So I won't chase through all the conformal transformations here, but the conclusion of that is that this pseudo-state, rho tilde, is e to the minus pi k, where k is the modular Hamiltonian for half of a circle that's twice as big for the ordinary ground state. So that's positive. But then I also have to multiply it by theta CRT, where CRT is the CRT that does that, okay? And then I actually also have to throw in t again. Okay. So I won't try to derive that for you. But this is the formula that's true for this rho tilde and any 2D CFT. And you can see it's not positive. So this is unitary, because there's two t's, right? So this is anti-unitary and this is anti-unitary, but the product is unitary, okay? So what this pseudo-state is a positive operator times the unitary, right? And so we just, when you compute things in these theories, you often end up computing them in a pseudo-state, which is a positive operator times the unitary. And that's just to probe the theory. Again, it's not modifying quantum mechanics.
What are you going to learn about the theory from?
Yeah, so you can study. Yeah, so I think the way I was thinking about it is you can study the algebra, because I can put O1 and O2 here, right? And so the algebra, so I can study the algebra in the pseudo state, even not, without it needing to be an actual state. Yeah, in the paper we do more of that, so I'm not going to inflict it on you, but we compute, all the Whiteman correlators and everything in the state, and you can check that they're consistent with the canonical commutation relations. You can see various things about the causal structure of these. They're consistent with the idea that things are independent and space-like separation on the slice. That kind of is what the canonical commutator would say.
So you're assuming that this operator is stated well defined, even though it's not positive on the local space.
Yes. Yeah, so the idea is this, this operator, so these operators individually are defined on this sort of half Hilbert space of the Rindler thing. But then because of the combination of these two is basically a spatial reflection, right? It's basically CR if we pretend that t squared is 1, sometimes it is, right? So that's what makes the combination a good operator on the Hilbert space with the gluing that goes the other way. Okay. Let me now try to get to the fun stuff, unless there's anyone else wants to complain about this. This is just to kind of warm up and get used to the idea of doing quantum field theory in this kind of geometry. All right. Okay, so now I'm going to do an example from ADS CFT to try to convince you that you really have to tolerate these things.
Just to double check, you're starting off from the Euclidean path integral on the right side, right?
Yeah, on the right side is Euclidean. Yeah, I'm using a Euclidean path integral to define the pseudo-state. But then I don't do it because I don't want you to suffer too much, but then we compute the Lorentzian correlators in that state. And you can see that they're sort of reasonable. But I won't try to define reasonable because that would take us into 15 minutes of Whiteman versus Schwinger or whatever this kind of thing. So, and it's more fun to do ADS CFT. Okay. So let's first just remember a few formulas about the BTZ black hole. So this is ADS CFT. So the Lorentzian BTZ, right, is lots. Okay, let's think in classical coordinates where t goes that way and x goes that way. There's also the Euclidean version of BTZ, where you can compute the partition function z of beta, which in the gravity variables is e to the pi squared over 2g beta. Or if you write that in terms of CFT things, it's pi squared c over 3 beta. That's the central charge. Now I'm going to brutalize this geometry to turn it into something more fun. So I'm going to do an identification. So I'm going to take each point. So here phi, so BPZ is this times a circle, a spatial circle, right? So this phi is the angular coordinate on the spatial circle. I'm going to identify this with minus t, minus x, and phi plus pi. So, I reflect both space and time, and then I translate by pi along the spatial circle. So this is freely acting. There are no fixed points because the rotation by pi always moves you somewhere else on the circle. And of course, and this obviously squares to 1, so this is z2. And so when I quotient, it's going to give me a smooth space-time, which is kind of half of this with some identification. Okay. Now, just for people who know these things, if I had put plus here, this would be the so-called RP2G Okay, it would be a sort of standard thing that people do, where it's a state in the CFT, which is prepared by the CFT path integral on the Mobius strip. Okay. So it would be a sort of non-orientable space-time, but time-orientable. With the minus t, it's orientable, but not time-orientable. And in fact, we can kind of draw what it looks like. So I'll draw 2 different pictures. So one thing it is kind of half of the BTZ, but then there's some sort of funny thing going on in the center. So it's now one-sided geometry, right? Because this minus sign exchanges the 2 boundaries. So I get rid of one of the boundaries. So the boundary is now there's now just one asymptotic ADS boundary. It's the cylinder. But then this point up here is identified with that point down there, but shifted by pi on the circle. Okay, so there's something kind of funny going on here. Like I fall in here and I come out there. Okay. You know, I'm a poorly falling observer. Here I come. Oops. Now here I suppress the circle. I can actually draw the whole thing not suppressing the circle like this. So you can think of this as the geometry in between 2 cylinders.
So can you do this again, including the sound effect?
So I fall in here going forward in time.
Yeah. You were going forward in time.
I was going forward in time, now I pop out, and I'm going backward in time, and I hit the past singularity. But in fact, the past singularity is connected to the future singularity because these 2 points are identified.
So Daniel, with the usual RP2G how do we think of it as prepared by CFT on a Mobius strip?
Yes.
Like what's the, this is comparing some density matrix?
No, that's a pure state. The RP2G is a pure state.
Yeah, that's what I thought. So what's the...
No, the CFT path integral on the Mobius boundary is where the state is. You can think about it as the disk.
Sorry, I see.
Yeah.
Okay. Yeah. Good.
Yeah, so that one is more conventional. This one we're going to see is one of these pseudo states again. So in this picture, right, the outer cylinder is the ADS boundary, right? So it's just one totally conventional, globally hyperbolic boundary geometry, our favorite CFT2 boundary geometry. So this is a totally valid asymptotically ADS3 solution, okay? But then in here, this cylinder now, I remove everything inside, and then I do an antipodal identification here like that. And if you think about it, the cylinder with the antipodal identification is again just this Lorentzian Mobius strip. Okay, so that just gets us back to our friend, the Lorentzian Mobius strip. So in particular, we see that there are circles where I go around the circle, I come back, and now I'm going backward in time. These are the same geometry. So I claim there are states like this in the CFT Hilbert space. Let me now try to convince you of that more quantitatively. Oh, I should say, by the way, so of course a thing you could worry is that this would just totally destroy boundary causality. That's actually not true here, because any causal curve that starts and ends at the boundary never meets this funny Lorentzian Mobius strip here. Another way of saying it is that this so it doesn't have closed timeline curves, but it has self-intersecting timeline curves, which I submit are just as bad. But the self-intersections are always behind the horizons, so there's no violations of boundary causality. Of course, that has to be the case. If boundary causality were violated, that would be unacceptable.
So this construction excludes anything that would have started from Caltraffic wall type of.
Yeah, well, so, yeah, that's a different thing, because that, yeah, there if you couple the two boundaries, you're not really violating boundary causality.
Right.
Yeah, so here I'm not coupling, the boundary is totally local, right? It's just the usual ADS city boundary.
Yeah, it's just that you were saying you can't go from the boundary to the fine sphere and then back out to the boundary, but in Caltraffic wall you'd be able to things like that.
Yeah, so you could try to play games by turning on backgrounds to try to make this thing visible. I think as long as you throw in as long as what you throw in is obeys the null energy condition, it'll just push this further in. Just the horizons will move out, right? Yeah, in fact, maybe I should say, so one could imagine some chronological censorship conjecture, which we tried to formulate in the paper, saying that if you have self-intersecting timeline curves, the intersections always have to be behind horizons. And we have some attempt to prove that based on topological censorship, which is a list of potential theorem in GR. I found various fights in the literature about whether the theorem is really true, and it's not my job to fix it. Anyway, there's a paragraph in the paper about chronological censorship. Okay. So that's so that's what we were doing up here, right? This is the Lorentzian picture. There's a Hilbert space on this slice, or on other slices that you can construct. You can compute correlators, etc. You again have the problem of having no natural state. Okay, and so if you want to do computations, you have to introduce a pseudo state. And of course, the natural pseudo state to do is to take the Euclidean BTZ and just do the same identification. So the pseudo state that you would get would be something like this. This is a bit heuristic, but basically fine. And then you have some identification like that, where again we understand that the identification also includes a shift by pi in the spatial direction. So this defines some pseudo state, phi f, rho tilde, phi I. And in fact, here we can figure out what the boundary description of the pseudo state is. So if you think about it, so if we started here, right, so this was going around this, right, was beta. So doing this is beta over 2. And then remember, these are identified, but with a shift by pi. Okay, because it was this shift by pi. And so what that picture tells you, if you stare at it long enough, is that rho tilde is e to the minus beta over 2h times e to the I pi j, where j is the angular momentum going around a circle. This is now a boundary thing, right? And again, you see we've got this pattern of a positive operator times a unitary. Okay, so that's kind of the theme of these funny geometries. Now, actually, here I can do even better. So let's define a partition function.
Excuse me.
Yeah.
You said before, if I understood correctly, that if you don't do the time conjugation,
Yeah.
then you would get a positive correlator.
Yeah.
Is that right? But
Yeah. In fact, I'll get a pure state. Yeah.
Because you get just a phase instead of you.
Yeah, because the identification doesn't glue things here and here. Then it just glues things here with other things here. So then it's still a pure state. It doesn't mix the broad cut.
Okay.
Yeah. So let's define a quantity ZCFT to be just this trace of e to the minus beta h over 2 times e to the I pi j. So it's a CFT quantity. We can also compute the same thing in the bulk. Okay. So actually the bulk calculation is very easy because this is just a Z2 quotient of the B to Z. So I just take the action and divide by 2. All right. So lucky me, I told you the action already. So this is e to the pi squared c over 6 beta. Right, that's the bulk contribution from this thing. Oh, I didn't say the name. The name we give to this is the CRT twisted black hole. I think it's a kind of reasonable name for it. So this is the Euclidean CRT twisted black hole. This is e to the minus the Euclidean action of the Euclidean CRT twisted black hole. Right. And then to see whether this is really contributing, let's now compute this in the dual CFT and see if we get the same answer. So to do that, you can observe that this thing is really just the CFT on some sort of tilted torus, okay, where you go by beta over 2 in this direction, and there's a shift here by pi, and this length here is 2 pi, right? And then you identify like this. That's what this is in the dual CFT. And so to compute anything like this, so I'm going to be interested in the high temperature limit, so small beta. So to compute things like this, of course, you do what I like to call cardiology. Is Cardi still here, by the way? He was here for a long time. Okay, that's too bad. Yeah, so you do cardiology. This kind of cardiology I'm good at, not the other kind. So to do cardiology, so you can write this in terms of a complex parameter tau, right? And so if you kind of stare at this picture for a little while, you convince yourself that the complex parameter is I times beta over 4 pi. And so then I want to compute the CFT partition function on the torus with this complex structure parameter at small beta. So yeah, maybe, I don't know, maybe I'll spare you the details. So you do, you know, S, then 2 T transformations, then another S transformation, and you find that Z of 1/2 plus I beta over 4 pi is equal to Z of I, oh geez, let me check, over, I think, beta, I think maybe with a pi here, something like that. I think that should be right. And this is now the low temperature regime, where you're just looking at, which should be dominated by the ground state. Okay, and we know the Casimir energy of the ground state, and so that we find that, guess what, this is equal to pi squared c over 6 beta. So what that shows us is that for this funny computable, the CRT twisted black hole is the dominant saddle point. Okay, so if you don't include it, you are out of luck, and HEP-QIS is wrong. Yeah.
Hey, should one read too much into the fact that the result is positive? As in, did you determine, so for instance, in the Cardi formula, you just took the vacuum Virasoro character that has some all-loop determinant.
Yeah.
Is that a real and positive as you wrote?
I didn't
You
try
didn't include it,
yeah,
but
I didn't try to think about the corrections to this. I just tried to get the exponent. So I'm not going to guarantee that it's positive. It may be, but yeah, I guess we should think about whether it's a theory with fermions or bosons. So if it's a boson theory, yeah, even then though, I guess this is plus minus, right? So it doesn't need to be positive. No.
yeah.
I don't think it needs to be positive. Yeah, I mean,
Well, I'm asking whether in this Cardi derivation you are able to derive that.
I didn't try. I just tried to get a leading exponent. Yeah. If I had a specific expectation for it, maybe I'd be motivated to try to compute it.
So this is really just a sort of Euclidean CFT partition function on some torus with some tau, right?
Yeah, that's correct.
So normally we would say the gravity calculation of that is just some Euclidean thing that fills in the torus, and we sort of wouldn't get too confused about gauging CRT or anything like that. Is that because you're not trying to give Lorentzian interpretation there, and you're trying to give Lorentzian interpretation?
So I'll make 2 comments about that, right? So one is that, so of course, what most people, I think if you ask a random person who thinks about this stuff, how should you think about this? They would say it's a BTZ black hole with the imaginary chemical potential. So that's another saddle point we could consider, is the rotating black hole with the complex chemical potential. That's a sub-leading contribution to this one, okay? Now, remember, I was really using this to define a state, and I can take correlators in this state and continue them to Lorentzian signature, and they should give me the correlators in this geometry. Now, I'm kind of lazy, so we didn't do this computation yet, but I think Tokiro is trying to do it. You could certainly try to sort of use the identity Virasoro block for this funny torus and see if you match on to, so I mean, we already computed the bulk correlators here and see if you can match them in the CFT, the Lorentzian correlators. It kind of has to work, so, but one could say that that's a more explicitly Lorentzian match.
Just to be clear, because possibly I'm missing something, if you just, this thing is just some SL2Z, the Euclidean saddle is just some SL2Z transformation of a thermal Euclidean ADS. Or
yeah, but if you think about taking the time slice here and chasing it through the modular transformations, it'll end up with something weird when you read the torus this way. So it's an analytic continuation that would be pretty weird from the point of view of the vacuum, the low energy limit. The analytic continuation is natural back in this SL2Z frame. So I just did those to be able to compute the partition function. Yeah, I think you can probably also say that even for the ordinary BTZ calculation without the pi, there are other SL2Z images which are in principle supposed to include it, and I think probably one could argue that some of those are including geometries like this, which are subleading in that case, but still may be there. We didn't try to make that precise, but that would be a natural thing for someone to try to do. Okay, I want to get to the quantum cosmology part because that's pretty entertaining. So how are we doing on time? 2 minutes? How strict are you guys? It shouldn't be more than 5 minutes just to get to the fun parts. So. Well, okay, depending on how much people want to fight with me. So now we get to the part where we start messing with quantum mechanics. In a closed universe, all states are gauge invariant. So in electromagnetism, we're familiar with that, right? You integrate Gauss's law. Say you lived on a big 3-sphere. You integrated Gauss's law, it would tell you that the integral of the charge density over all the space is 0. That's true for discrete symmetries as well, as we saw in the pictures earlier that I was drawing, right? You have to project on the singlets on the circle. Now, let's think about if we're doing quantum gravity in a closed universe, then as we discussed, then we always should have CRT symmetry. At least for me, that's an axiom. You always have CRT symmetry. It's also an axiom for me that you don't have global symmetries, so it's gauge symmetry. And that means that the state of the universe, the wave function of the universe, has to be CRT invariant. So let's see what that tells us. Well, here's one thing that it tells us. So say that psi and phi are CRT invariant states. And let's make a linear combination of them with some coefficients, and then act on that with CRT, which I'll write as theta. So if I want this to be a physical state, then this should be equal to A psi plus B phi. But since theta is antilinear, because it's CRT, it's actually equal to A star. And then remember, these are invariant, so then I can just get rid of the psi, the thetas, plus B star phi. And so in order for these to be the same, A and B have to be real. And so what we learned is that physical states form a real vector space.
You don't allow overall things?
No. When you say that the states are gauge invariant, you mean gauge invariant. It's not enough to be invariant onto a phase. Now, if this sounds totally nuts, right? Because, all the good stuff in quantum mechanics, right? The double slit experiment, right? Shor's algorithm, Stern-Gerlach, right? All of that is about interference of phases in the Hilbert space. And here I am telling you that actually, no, the Hilbert space is real.
This is a global statement.
It's a global statement.
It's not what we deal with in a Stern-Gerlach experiment.
Yeah, well, it's not really going to be a problem, but we have to understand why not. Yeah. Right. So you could say, therefore, Daniel, you're an idiot. You must have made a wrong assumption somewhere. But I actually don't
He's
think.
expecting to be driven out of the room by us.
Yeah. So let's ask. Right. So we could ask, why doesn't this destroy quantum mechanics? So the reason it doesn't is something which, for people from quantum cosmology, is somewhat familiar, I think. Which is that in quantum cosmology, you need to have a clock. So let me try to show you how clocks can save quantum mechanics, even in a real vector space. So let's say I have a quantum system living in a closed universe somewhere, and it's in a state psi. Well, and let's say that psi is not CRT invariant. Well, I can always make a CRT invariant state in the following way. I do a superposition, and then I have a clock system which is going forward in time, times the state that I want of the system. But then there's another branch of the wave function where the clock is going backward in time, and then I have the CRT conjugate of the state, where I actually have to be careful, I should say theta s. So I have CRT, I can just on the system. And this is clearly a CRT invariant state, at least if CRT squares to 1. So if it doesn't, if there's fermions, I have to write more stuff. So let's just say CRT squares to 1 for this talk. Similarly, so say that I want to, for example, do the measurement. I want to see whether or not the system S is in the state chi. All right.
So can you say you got the clock going backwards?
Yeah, so plus is the clock going forward in time, minus is the clock going backwards in time. And then this is the state that I want, and this is the CRT conjugate of the state that I want.
What is the
Because the full CRT acts on the clock as well.
Oh.
So this is the theta that acts just on the system. You could complain that's not a good approximation, and we're going to discuss that in a second. But for now, let's assume that there's a theta s. Then you can also, so now let's discuss an observable where I want to see whether the system is in state chi or not. Well, again, that's not a CRT invariant observable, but I can make a CRT invariant observable by doing the following thing. I check if the clock is going forward in time, and if it is, then I check if the system is in state chi. But if the clock is going backward in time, but then I also check if the clock is going backward in time. And if it is, then I check if I'm in the state theta chi. And that's again clearly a CRT invariant observable. So this lives in a real vector space, this acts on a real vector space. And yet, if you work it out, you compute psi tilde, p tilde, psi tilde, you just get what you have to get, which is the Born rule. You take the inner product of psi and chi and you square it. So you get just what you would have gotten by ignoring the clock altogether and just using the ordinary rules of quantum mechanics. And so this psi could live in, right, it could live in a complex Hilbert space, right? This S could be a complex Hilbert space. It's only the full thing that has to be living in a real vector space. And so something that's analogous to this is like an electromagnetism, right? If you live on a big sphere and you want to study this 2 to 2 scattering of electrons, right? So, well, that's not a physical state because there's 2 electrons and the charge is -2. So to get a physical state, I have to put 2 positrons somewhere else in the universe. And that's the clock, okay? Now, you could say, Daniel, this is stupid, this is bookkeeping, right? Like, this is just an accounting trick. What you showed me is that you can take any quantum system and make it look like it's living in a real vector space. Okay, and that's true, I did show that, right? But the key thing is that the clock has to be part of the system too, okay? Just like the positrons. And in the example with the 2 electrons scattering and then you put the 2 positrons over there, those actually affect the electrons, right? The electrons can feel those 2 positrons because you're in a universe of finite size. And that will affect the result of the experiment. It'll be a sort of finite size effect that will only go away in the limit that the universe is infinitely big. And similarly here, right, what I did here was kind of too quick because I neglected the fact that there could be interactions between the clock and the system. And if there are, then this theta s operator doesn't really make sense. It's only the theta that acts on everybody that makes sense. Okay. So let me try to say that more provocatively, what we have learned. We have learned that in the real Hilbert space, the genuine Hilbert space of quantum gravity in a closed universe, the Hilbert space is real. And the idea that in quantum mechanics you have a complex Hilbert space is only true in the approximation that the universe is infinitely big. And when the universe has finite size, there are corrections to the complex Hilbert space of quantum mechanics, which come from the fact that you're really in a real Hilbert space and you don't really have this theta s, you only have the theta that acts on everybody. And you have to use that.
So, but here it's important for you, there's no boundary, right?
Yes, it's important. Yeah, so when I say closed universe, I mean no boundary. That's essential. Yeah.
So some might have said that that's sort of a one-dimensional Hilbert space anyway. I mean, if it's a closed universe.
Oh, I'm not one of these people who thinks it's one-dimensional. I know there are these crazy people who think that. But, I'm willing to, it may be that it doesn't make sense at all. That's certainly possible. You know, the idea that you just can't talk about quantum mechanics on these global slices. I mean,
I just mean that, like, if you think of it as a tensor network, it's other numbers.
I know these various arguments that it should be one-dimensional, but I'm skeptical because it seems to me that, I mean, I do believe that the Hilbert space dimension can be much smaller than you want, right? That's the non-isometric code. But the non-isometric code only works if the space you're mapping into is still big. If it's one-dimensional, I don't know how to think about it.
All the interesting physics will come out of dividing that system.
What does that mean? It's one-dimensional.
Well, it's in one. What it means is that you can't act from the outside to change the state.
Darren, do you think Chern-Simon's theory on a sphere has interesting physics? It's a one-dimensional Hilbert space.
No.
You don't think that?
Yeah, I mean, maybe you can have a phase, but that's kind of, at most you have a phase.
You have Jones polynomials.
Do you think it has the depth of human experience?
I don't have the depth.
Yeah. Or I could say, can you make a Turing machine? I don't know.
You can make those polynomials.
So look, I don't know, right? I mean, so it could well be that.
Yeah, I bet Jones polynomials are Turing complete.
And by the way,
I'm sure somebody's written a paper saying that.
if not really,
If not, we will.
Yeah. But I mean, actually, if you think the Hilbert space is one-dimensional, then it's even worse. You don't even get the phase because it has to be real, right? So,
right.
So you have a plus or minus. You have a classical bit, a plus or minus, I guess, is all you have.
So I'm talking about the Hilbert space on a Cauchy slice.
Yeah, but a complete Cauchy slice.
That doesn't have to be one-dimensional.
Well, I don't know. It depends who you talk to. Some people say it does for a closed universe.
I thought the baby universe Hilbert space was one-dimensional.
That's what I'm talking about, a closed universe with no boundary. We could call it, I mean, I don't know if you want to call it baby universe. But yeah, I mean, I think the people who believe that would say that a closed universe on a global slice, like De Sitter on a global slice, has a one-dimensional Hilbert space. So I don't know if that's true, and I don't know if the notion makes sense at all. But if it does, okay, then what this would suggest is that in trying to find the holographic dual, right, so you could say, who cares, right? I mean, these effects are very small. We're never going to measure them, even if we live in a closed universe. I mean, that's all true. But if you're trying to find the holographic dual of quantum gravity in a closed universe, then this would say you should look for a real vector space. And I think that lesson may be correct. Now, it may also be correct that it doesn't make sense to talk about the quantum mechanics of the whole universe, right? Quite possible. So that's why I don't push this too strongly. But to the extent that it makes sense, I think it should be a real vector space. And that actually comes up. So for example, this comes up in the old story of the Harlow-Hawking wave function. There was this expanding branch and contracting branch, and people fight over you include both, you don't. So this would say you have to include both, right? So it would say Harlow and Hawking are right, and Vilenkin is wrong. So for people who know the history. Anyway, I'm over time, so I should stop. But happy to talk more. I'm here tomorrow also. Questions?
If you consider like an actual cosmological model, what do you expect? So for instance, in De Sitter, would you expect that correlation functions that, let's say, are able to differentiate between purely real phases and complex phases are suppressed by e to the minus S De Sitter or something like that?
Unless they're addressed to a clock, right?
No, but if the clock was part of your system, presumably you have the De Sitter.
Yeah, so yeah, and when you do this in de Sitter, the clock has to be made out of the matter fields in de Sitter.
That's right, so that's not a good approximation, right?
Well, it is if the universe is big. So
That's right. So what I'm asking is what's the error rate coming from the fact that the universe is not big for a correlation?
yeah, I think there will be power corrections like 1 over the entropy.
I see, not exponentially.
No, not exponential. Yeah, because this is kind of a dressing issue, right? So, not being careful about the dressing is something that bites you in perturbation theory, not just non-perturbatively. It'll also show up non-perturbatively in terms of the choice of the state, right? So in this thing I said about the expanding and the contracting branch, that's a kind of a non-perturbative thing, right? The fact that there's another branch of the universe that's contracting, you kind of only detect non-perturbatively. But I would say you have to sum over it to get a physical state.
I think that's not, so I don't think it's quite right that this is built into the Harlow, into the no-boundary proposal, right? Because you can also compute the wave function as a function of the extrinsic curvature,
Yeah.
and then you pick up only one, you only pick up one branch. And I think what you would be saying is that that's just not something you're allowed to do anymore.
Well, no, I would say you're allowed to, right, so the state of fixed extrinsic curvature is not CRT invariant.
Yeah.
So you have to...
What you would be allowed to ask is about a state of where the extrinsic curvature is either, I guess, one or the opposite.
Yeah, that's right. You can have superpositions that are fine.
So you're not, the formalism doesn't stop you from asking about just one specific extrinsic curvature corresponding to, say, an expanding de Sitter space. It doesn't,
No, the bulk of it, if you say CRT is gauged in the bulk, it does prevent you from...
Yeah, sure. I'm just saying that's not,
But you could
that's
treat it
not already built into the...
well, it actually almost is, right? So yeah, maybe this will be the last thing I say. So our story about this treats CRT and separately from how it treats R and CT. So our story is that the sum over topologies in the Euclidean path integral automatically gauges CRT. I didn't have time to explain that, but that's true. And so when you think about the Harlow-Hawking state, what happens is you're trying to compute the state of the universe, you want to compute the wave function of the universe on a slice of radius day.
If you specify that, then that happens to work out.
No, but I'm saying so the summing over topologies would say I should sum over both that and that, right?
They have the same topology, but yeah.
Yeah, they have the same topology, so it's summing over geometries, right? So yeah, when I say I don't just mean sum over topology and geometry. So these have the same topology, but this is actually the CRT conjugate of that.
Right.
And so if your rule is that you should sum over everything I should put here, then you should sum over both of those.
But then the formalism, this is accidental to the fact that if you ask about the wave function as a function of the scale factor, then that happens. But if you're just, it's just as legitimate to ask about it as a function of the conjugate variable, which is the extrinsic curvature.
Well, it's not. No, but it's not legitimate to ask about that if it's not CRT invariant, right? So.
Good. Again, I'm just trying to emphasize that is still an extra condition that you are imposing on.
Yeah, I'm imposing that it's a gauge symmetry because indeed my motivation that there are no global symmetries comes from logography.
It's something that you're doing.
Oh, sorry. No. But so I think it's the usual thing, right? So yeah. Like, let me think if I can say this. Sorry. Now this is getting a bit more into the weeds, but. When you really think about what's gauged, right, it's a statement about what kind of gluing is allowed in transition functions. So it's a bit easier to say it for T or R separately. Actually, let's be in Euclidean signature, so R and CT are the same thing. Then there's a question of do you allow orientation reversing gluings when you construct spacetime or not? And if you allow that, then R and CT are gauged. And if you don't allow it, then they're global. So that's the definition that makes sense in gravity. And that's a distinction you can see already at the level of the path integral. Now, if you try to do something where you say, well, what about CRT? So in Euclidean signature, CRT is part of the identity component of the diff group. So you basically don't have a choice. You have to allow gluing by rotation by pi, because a rotation by pi is just 2 rotations by pi over 2, or it's 10 rotations by pi over 10, and you can get as close to the identity as you want.
What are we doing to work here?
And gluing different coordinate patches together, right? So
I don't need many.
in this particular example, you don't. But in general, to have a rule for the path integral that's consistent with locality, you have to say what are the set of geometries that you sum over. And part of that, for example, is saying whether unoriented geometries are allowed or not. And
I still don't see what would have prevented me from evaluating the wave function of the as a function of A dot or the extrinsic curvature, and
yeah, so here,
getting,
well, yeah, so here's a bit semantic because the Harlow-Hawking state is kind of a definition. My understanding of the Harlow-Hawking state is you should sum over everything that you can put down here.
Exactly.
Maybe that's not the right definition, but that's
if you
my
had specified
understanding.
A dot, there would have been only one term, not two.
But does that give a wave function with real coefficients or
No, it doesn't. That's my point.
But if you
my
sum
point
here,
is that that's not built into. And I have nothing against doing that. We can do that.
I guess I don't understand why that state would be non-gauge invariant under CRT, which I think is what you're saying.
no, because the bra that he's projecting on is not CRT invariant. Because
Yeah, why is it not CRT?
because the extrinsic curvature is 2, then if I do a rotation, it becomes -2.
Yeah, but that's a
But I can do this in the gauge theory, right? I can
Yeah, you can-
I
you
can
can certainly-
insert some bra. I can consider some bra
Yeah.
that's just some particular gauge configuration that's not gauge invariant, and then I can compute inner products of it with gauge invariant
Yeah,
states
so-
and so on.
Okay, so maybe a
The
better
Harlow-Hawking state itself is CRT invariant.
Yeah, so I mean, they actually computed in this basis, if I remember correctly, and there's some story about the contour
So
that
they-
they choose, Harlow-Hawking.
Okay, yeah.
And they end up with this, right? And they computed but they also computed in the K basis, and it's the same, it's still this state.
I mean, Hawking and I computed it in the in terms of A dot.
Yeah.
In terms of curvature. We did that because we wanted to pick up one direction.
Yeah, but fine, but whether you sum or not doesn't depend on the basis you use, right? We can think abstractly. So you either sum or you don't sum.
Yeah, that's right. You could
Yeah.
still sum if you want to.
Yeah. I mean, and they said you should. Now, I don't understand their argument that you should sum, but they did have an argument. What they said is that when A goes to 0, they want the wave function to somehow be consistent with it being 0 when A is negative.
When you specify A as the argument of the wave function, then
Yeah.
it's pretty obvious you have to sum because there are some people two contributions in the path and you roll that down.
I mean, Valengan said that you should just do one, and we could, I don't know, this is a fight that's been going for 40 years, so I don't know.
That's not, the fight was mostly about the sign.
But there's also a fight about the sign and the action, that's right. But, I mean, those are related, because that sign has to do with how you analytically continue this one. Which one is expanding or contracting depends on the branch cut, so there's some, anyway, that's insight baseball. But, yeah, but I think that I think the right way, I tried to avoid this language in the talk, but if we really want to say this mathematically, the language for deciding what is the gauge group of the space-time gauge group is you look at the structure group of the tangent manifolds that you're allowed to sum over. Okay? So in general, transition functions live in GLD, okay, or GLD minus 1 comma 1 if you're in the Riemann signature. But then, for example, if you have a Riemannian matrix and Euclidean signature, you can reduce it to OD. Because you can do it, you can pick a frame in each patch, and then the transition functions are orthogonal transformations. Right? And now, if you want to, so in general, that's all you can do. But now, if you say that, for example, R and CT are global symmetries, then you shouldn't be allowed to glue. You shouldn't allow gluings that involve R or CT, and so you have to further reduce the structure group to SOD. Okay. And then you can only sum over oriented manifolds. So when you sum over oriented manifolds, R and CT are global, but when you sum over unoriented manifolds, then they're gauge. Okay? Now CRT is more slippery because it's in the identity component. So if you want to say, well, I don't even want to sum over, I want to reduce the structure group further from SOD to something that doesn't include CRT, then pretty much the only thing you can get is the trivial group, which says that the whole manifold can be covered in one patch. So you basically have thrown away the sum over topologies by saying that. So that is actually what canonical quantization would tell you to do. It would tell you to just do globally hyperbolic things. But I guess we think that's not all you should do. But the thing, like for example, if you write down a wormhole connecting two things, you can actually prove, so we have a proof in the paper, that somewhere in the transition functions there's a rotation by 2 pi. Rotation by pi. So you can't have a non-trivial topology without having rotations in the gluing functions. This is really not surprising. I mean, it's kind of obvious.
What statement statement would you want to make about like R and CT separately? Like should they, I mean, like, presumably they shouldn't be allowed as a global symmetry?
Yeah, so the options are they're not a symmetry at all or they're a gauge symmetry. Those are the options. Yeah.
So if they are a symmetry of your theory, then you have to sum it on or whatever.
That's correct. Yeah. You can always play the game
symmetry of your boundary theory.
Yeah.
If I was talking about the bulk theory. If you tried to define quantum gravity, it would have been a bulk theory that has R and CT.
I mean, in low dimensions, you can play this annoying game of saying that they're symmetries of the ensemble, but not of the instances. So that's what it would mean for them to be global symmetries. I think in higher dimensions, those words probably make sense.
Sorry, I just want to make sure that I didn't misunderstand, or I probably misunderstood it. Are you saying that gauging CRT enforces that you have to sum over topologies? No, right?
I think I am saying that, yes.
Can you describe that again? I think I didn't quite understand that.
Well, I think what I'm really saying is that gauging CRT doesn't really make sense unless you gauge all of the identity component of the diff group. So then you have to allow, and that means you should allow gluons that are in SOD. And that is equal to summing over all oriented topologies. That's kind of the argument.
Isn't the right statement just that gauging CRT was automatically happening when we were gauging diffeomorphisms?
Yeah, that's basically I mean, that's kind of what I'm saying. Yeah. No, but, well, you can do something slightly dumb.
Can I just hear what it is that?
Yeah.
I was just saying that we were already gauging CRT because we were gauging Euclidean diffeomorphisms, and that includes CRT.
I think there's a sense in if you do the canonical formalism, you're not gauging CRT. Because just why would you? You don't go to Euclidean signature at all. But I think from the path integral point of view, it's almost stupid to talk about not gauging CRT. That's kind of my attitude. So it is treated differently than R and CT, which is a little confusing.
I guess I just don't quite understand. Suppose that we're in 2D and we restrict ourselves to doing the path integral over this topology.
Yeah.
There, the diffeomorphisms do gauge, even on the disk, gauge CRT. What forces us to include genus 1? What forces the diffeomorphisms to have components that are disconnected from the identity, I think is what you're saying. There's something that forces diffs.
No, there's not. No, because if you just gauge CRT, it's only the identity component.
Yeah.
So that, I mean, I think I'm saying the same thing as Jeff, which is just since it's in the identity component, if you don't gauge it, then at least in Euclidean signature, then just gravitons won't even make sense, right?
Yeah, I understand that. I guess I just don't understand what forces us to include genus 1. As an example.
Well, if you take these rules for defining a non-trivial bundles, right? Then you can view that as a non-trivial CRT bundle. You can also just view it. I mean, the right thing to say is it's a non-trivial SOD bundle, right? Yeah, kind of separating out CRT is a little bit funny. You just say that it's a non-trivial SOD bundle, and if SOD is gauged, then you should include it. That's it.
I think the flow of logic is going the other way from you think. It's not that you need to include genus 1 things to know that you're gauging CRT. If you just worked in Euclidean signature, Lorentzian signature, and fixed the topology, then it's not obvious that you have to gauge CRT.
Yeah.
But if you want to include Euclidean wormholes in your theory, then sort of, morally you're having to include Euclidean stuff, and once you're including the Euclidean stuff, then it's in the identity.
Okay, I think I can say this better. So the thing that's confusing here is that in Lorentzian signature, CRT is not in the identity of the component of the Lorentz group, but in Euclidean signature it is. Okay? So if you just do everything in Lorentzian signature, you can have a perfectly consistent theory where you don't gauge it. But if you want the Euclidean path integral to mean anything, you better gauge it. I think that's probably another way of saying it.
No, I agree with the fact that it should be gauged just from what Jeff said, which is that it's an element that's part of the...
But not in Lorentzian signature it isn't.
Yeah. I'm just talking about Euclidean. What I guess I wasn't entirely sure, but maybe we can discuss afterwards, is why that forces us to also include topologies that are not trivial.
Because well, I'm saying if it's a gauge symmetry, you have to do that. Maybe are you asking me to explain why there are no global symmetries? It sounds like that's what you're asking me to
I think
explain.
Luca thinks that you said if you're gauging CRT, that then implies you must include non-trivial topologies.
Well, I think
you said
I am saying that.
Yeah, you're saying that.
Because the non-trivial topologies are non-trivial SOP bundles, right? That when you gauge the symmetry, it means you have to sum over the bundles.
So what's
Right?
wrong
That's what
with-
it means. I mean, that's how I define gauging the symmetry, right? Is summing over all the bundles.
Can't you just like say we're including any SOD bundles with some fixed topology?
Yeah,
Like maybe
that's what we would do in the
that's
case.
No, but that's like saying I'm including instantons with instanton number 3, 5, and 7, but not 2 and 4. You know, I think it's inconsistent with locality. No, so yeah, I think it's important. Maybe another way of saying this is that for the rule to be consistent with locality, I think you need to be able to articulate it as a statement about the structure group of the tangent bundle. And the rule that you include, you know, genus 7, 2, and 27 and nothing else is not a statement you can make about the structure group. I think that would not be consistent with locality. In fact, we have some theorem we proved to try to motivate that, which I can tell you later, but I don't want to bore everyone with 2D geometry. Yeah, so it's just like summing over magnetic monopole number or instanton number in field theory. If it's gauged, you do it, or you're violating locality. You know, or locality meaning that anywhere I can put the U of G operator, I better put it when I do this number.
Okay, are there any other questions? If not, let's thank Daniel again.